Go for like 5 hour energy.
No, that's
That's,
just
that's
two
the only
copies.
hour I want to do.
That is 2 large copies. If I hurt, it feels like it's gonna stop.
Like, five hours before the exam, you take 5 hour energy.
Oh yeah, I'll finish the exam in 10 minutes and then die.
In the middle of the yeah, as he's walking out the door.
Boom, just off I go. Hey.
Then you enter a nice dreamy world.
Oh yeah. Bro, I don't have to do any more assignments if I go into cardiac arrest. You guys are thinking straight.
From like 5 on, I'll probably just be chilling in the
If you die, you don't have to work anymore.
Yeah, don't worry, fall break is coming.
I know.
It was like, I think the weekend before last weekend. Work at college if you're dead. The weekend before last.
I'm in your next section. I just had a modeling question.
Yeah.
I feel that.
We were talking about whether or not we'd start going to church and God gave us a heart attack. We were talking about whether or not we'd start going to church if God gave us a heart attack so that we didn't have to finish the homework.
Honestly, I would. I would start going to church again.
Yeah, and like,
This is making me bad.
bouncing off the walls.
Not less bouncing off the walls, the more I'm functioning.
Barely.
Barely. Oh no, this morning I was dead.
Man, your workload is so intense.
What?
Your workload is so intense. I can see why you're getting started on stuff early. I have no classes on Tuesday because I had 6 classes on Monday.
Oh no, I have a lab
And they're all
on
back to
Tuesday.
back.
I have a lab on Tuesday and the lab report's due the week after during
All right.
break.
So,
So I
okay,
have
so
to work
fall
on
is
my
on Wednesday.
Oh, it's so bad.
I can hear you, Professor.
All right. So please unmute yourself anytime if you have any questions or comments, okay?
Dynamics,
All right, as usual.
prop, structure,
Okay.
6, about 5 in a lab. I contemplated dropping a class, but I was like, no,
Somebody's
I'm
deep
running
side,
this.
huh?
I don't get it because I have 1 class in the lab this semester, 17 credits. Next
Doing
semester,
good?
6 classes, 2 labs. I think I'll do in the lab, still 17 credits.
What, data
Everybody's
entry?
in? So let me just take
Some sort of like black magic or something.
Data acquisition.
I've been doing that.
That lab.
This
Okay.
semester,
You just mentioned.
5 classes and 2 labs. 6
Alright,
Previous semesters, I both had like 5 and 6 classes.
I don't like
On
my
segmentation or something like that.
because of how
We should have to take that out too.
every semester to go 17 credit hours apart from first semester freshman year because I know you haven't completed a lot of your prerequisites and you can't get through them without doing that. But I have so many classes that I transferred from dorm room or AP basically I got out of a lot of my lower level courses, which is a godsend. But the problem is I only took 14 credit hours because I couldn't get ahead on it. It's like, well, you've taken all the gen eds and fill out your credit schedule first year, but it's like, oh, you're gonna get further, any of your engineering courses,
everyone.
science courses, well, too bad. Like, you
There are a
haven't-
few announcements to begin today. Of course, you guys know that we have midterm exam on Wednesday. And this is quiz 6, but this is way after fall break, so you probably don't care. That's all right. But announced already anyway. So be aware, be aware. So do you have any like last minute questions of midterm exam? Well, go ahead. Go back.
It's more of like a broad question, if that's okay.
Yeah, that's fine. I may not be able to answer that, but go ahead.
It's like, can you go over like one problem from each section?
No.
Like A1 and Yeah.
Possibly.
Yeah. Is he able to do it today?
Huh?
Today?
Today what?
Are you going over notes at 5? A5?
I'm gonna go over notes of A5, yes. I don't wanna waste one lecture period to like the problems you already have access to solutions.
Yeah.
I posted all solutions right now, everything including homework of A4. Yeah.
Since it's closed notes, we can't bring the standard atmosphere tables, so if we're given a pressure, we'll be given.
Probably yes. You
Okay.
don't, unless you want to memorize all the tables. No. No.
16-page
No.
document.
Of course not.
Wow.
Yeah.
I don't even memorize those.
It's
Go ahead.
not possible.
So in
I used
quiz
it for
3,
the homework
when we
and
solve
yeah,
for the
it's
pressure
16
for
pages
part
long.
A.
Which one? Which one? Which one? Let's
Quiz
take a
3.
quiz 3. Okay, let's take a look at quiz 3. Okay, I'll go to solution. Okay.
Yeah.
Quiz 3. This thing.
Either one.
Quiz 3. Yeah. Okay.
Okay, so when we solve for the pressure, we get a number that is negative. That is the test section dynamic pressure.
No, it's a test section static pressure is a negative.
Okay, it says
Test
that-
section dynamic pressure is Q, positive always.
Yeah.
So right here, static pressure is minus Q, dynamic pressure is Q. If you add it together, it's 0.
Yeah.
That's the total pressure.
Right.
Throughout this line, total pressure 0.
Okay. So then P1 that we calculated is
You can calculate from this. Obviously, this is lower pressure side, this is 0 gauge. Starting from 0, 1 inch down, it's like a 0 plus law of oil times gravity times 1 inch divided by 12.
yeah.
And then here's the same pressure, and then from here to here is whatever the pressure here minus rho times law of water times G
Right.
times H is equal to some kind of negative value.
Okay.
Yeah, so that's fluid mechanics. I don't want to go over it.
Well,
Yeah, of course you know that. It's a manometer equation.
It says dynamic pressure.
Huh? Where?
Right
Test
there.
section dynamic
Wait,
pressure,
wait,
second
wait,
line.
It's test section.
it's
Well, because it's yeah.
that's
So this is negative of test section dynamic.
that's yeah. Okay, that was my question more. Yes. Okay, got it.
Thank you.
Yeah.
So this is actually close out this. This is static pressure. It's a negative of dynamic
Okay.
pressure. Sorry. Yeah, that's a good point.
So when it
This
asks-
is actually test section static pressure. Sorry. Which is happen to be negative of dynamic.
Okay.
You're cool.
The fact that you say it happens to be is not always the case, right?
Of course, you have to apply Bernoulli's equation to find out those things, right? If you apply Bernoulli's equation, it's obvious. This is 0 plus 0 is 0. This is minus Q plus Q is 0. This is 0 plus 0 is 0. So Bernoulli's equation. Right. Okay, it's a good point. Great point. I appreciate that. Any other question?
Oh,
Yeah, go
last
ahead.
one. Do you expect the exam to take the full 50 minutes?
If I take that same exam, 10 minutes,
Okay.
because I'm the guy creating the problem now, but
You just have the answer sheet right there, don't you?
no, I don't need that. Go ahead.
So you said there was gonna be 3 problems,
Yeah.
right? And it's gonna be units 1 through 4?
A1 through A4, yeah, that's the coverage.
Okay.
I'm not saying each one problem coming from each unit, no, anything like that, but coverage is A1 to A4. Yeah. Well, I'm trying to save it, right? Save it, okay. Make sure I save it. Okay, anyways, any other question? Because I have to fix it. I really appreciate that comment. That means you understand it. That's great. This is the skill set, real skill. You desperately want that kind of stuff. Go ahead.
Can I ask a question about homework 4?
Homework 4, yeah, the solution is positive though. Let's just take a look. Yeah.
It was A42C.
Which one?
A42C. I just had a question. I had a hard time articulating the difference between static and total pressure.
Static and total pressure. Static pressure at a given point is a pressure we would feel if we were moving along with the flow at that point. That's the static pressure. That means, what is the static pressure in this classroom? It's atmospheric.
Total and stagnation pressure.
Total stagnation, okay. Total pressure is basically addition of static and dynamic in terms of aerodynamic analysis sense. However, the stagnation pressure is a pressure basically measured at the stagnation point. Velocity happens to be 0 at that point. And then we assume it's the same thing, but it's not. It is the same only if the flow is 100% isentropic. So which one is a lower body, possibly?
It's gonna be the
Stagnation pressure, because that's the pressure you may shed off some of the energy which is non-reversible. Because total pressure is academic, period. But stagnation pressure is a pressure happen to be measured at the stagnation point. It is going to be total pressure if everything is isentropic, but things are usually not isentropic, so you lose some energy. So pressure tends to be a little bit lower on that point, stagnation point, lower than total pressure. But low speed, we ignore it. And then even high speed, we assuming isentropic, we ignore it. So that means in aerodynamics, it oftentimes says, well, P0 is a stagnation point, which is equal to total pressure, which you need to be very careful because we have assumption isentropic behind that statement. Okay, that's a good question too. Any other question? Those are the real knowledge, real skill. I love to hear those kind of discussion in this class. Those are the real skill set industry people love to hear. Okay, because those are the discussion you probably end up engaging with a real job interview. They may casually asking that kind of question. Then you go like, huh? Kind of saying, well, they never get that kind of job. So, anything else? Solutions already posted here. Everything is A1 to A4. So please study. Okay. Study means you're going to compare your work against my work, and then if you did something wrong, you redo it. Redo means redo. You're not going to learn anything by looking at my solution because it's not your solution. You assume that, hey, I can kind of look at professor's solution, memorize it, and I can do super A's on the exam. You can try it if you want to. Go ahead, find the wrong way. Go ahead, run the hard way. Okay. I don't have to prove it to you. Lots of people actually try and they're wrong. Okay. The only thing you can write it in exam is the things that you actually did it. Okay. Guaranteed. Because that's the only thing you know and you can. That's the skill. Okay. So don't assume you can pass the exam by hitting over, all-nighters, memorizing everything. It's not going to work, guaranteed. So I guess the question is, study means that you did solve all the problems all by yourself, 100% understood. Yes or no? And that's the question. If you did all of those things, this is not exam, it's entertainment. You probably have graphic throughout the exam time and turn it in and have an enjoy full break. If you didn't do that, I don't know, no comment. Any other question? Can I move into A5? Go ahead.
It's more likely that Unit 1 through Unit 3 will be on the exam, correct? Because that's stuff we covered way before.
More likely, what do you mean?
Well, like, we need to know Unit 4, obviously, for the exam, but it's more likely that Unit 1 through 3 will be more the majority of the exam. Does that make sense?
I'm neutral for that question. I stay neutral. More likely means your assumption. You can assume that way, but it's assumption. Because official announcement is given here, okay, updates. This is my official announcement. Coverage is A1 to A4, A1 to A4. Okay. Anything else? A4 is easy. What are you talking about? I mean, if you get one of those problems out of A4, you go like, yes. But it's easy. A4 is airspeed. I mean, that's it, right? You can do it. Suppose if I say, okay, derive the true airspeed out of high speed. No, you can do it. Easy. Because it's coming from energy. Solve it for Mach number. Plug in all of those constants. Make sure P0 minus P infinity is in the equation. Okay? That's it. So again, try to memorize all of those things seems impossible, but if you know what it is, it's easy to derive that kind of stuff. That is a skill set I want you to have. Memorizing is the term belongs to people who don't care about learning. They just want to pass this exam. Memorizing is not required, but my statement saying you need to know means much higher call. Hard to be an engineer. Anyways, can I move in to A5?
Please.
Any other questions? Can I move in? You can stretch out as much as you can, but can I move in? Can I? Okay.
Yeah.
Okay, let's move in to A5. So today is very, very important lecture. So I want to be very careful about it because this component is going to be quizzed on quiz 7. Very, very important. So I want to approach very carefully. Anyways. So I'm going to color code it first of all. So this is the page 4 I want to cover. Okay. So what I'm going to do today, I'm going to basically try to go all the way to the every single detail of how on earth the measurement of this pressure here at the location over the surface. I keep saying integrate from leading edge to trailing edge to determine lift and drag moment. Okay? So starting point is, let's just take a look at the wind tunnel testing. Okay, wind tunnel testing, let me just show you the picture here. So let's say you're going to get into the wind tunnel. Then you do this kind of testing. Okay? So this is a two-dimensional airfoil cross-section constant from this end to that end of the test section, which is called quasi-two-dimensional testing. That means you're not interested in three-dimensional data. You're going to squeeze out 2D results out of it. In other words, whatever the force measured out of this test model, you're going to divide by span, wingspan. That is going to give you lift and drag and moment per unit span value divided by Q infinity C gives you lowercase CL, CD, CM. So airfoil coefficients you want to squeeze out of this test. This is called quasi 2D test. You're going to do that. Guaranteed. Now, this is one of these very special tests that you're going to have tons of pressure tabs on the surface. Each one of them is connected to this tube and then connected to this thing. Of course, you know. What's this? This is what kind of manometer this is? This is not YouTube.
Differential.
This is just this is not differential. This is a vertical, just manometer. It's just a pipe standing up. So if you have a pressure, it's going to push up the gauge fluid, or well, suck the gauge fluid, push up. I don't know either one. Think about this. This is a differential gauge. No, it's not, because you're going to measure all the static flow. Static pressure is measured over the surface of different locations. So when you turn on, what happens? This kind of thing happens. Pressure distribution over the surface. Okay? That's what you measure. So now, if you measure that kind of stuff, you're going to predict the lift and drag moment. How to do that kind of stuff, I'm going to go to the every single detail today, so please stay focused, because this is mathematical full detail. This is probably the only time you're going to get such a thing. No one's going to show you that kind of stuff, guaranteed. Very unique, okay, derivations. And then I'm going to test you out on quiz 7. Okay, so stay focused. If you want to sleep, today is probably the best day. Of course. You're going to lose probably once in a lifetime opportunity, you're going to lose it if you sleep it a day like this. Anyway, so I'm going to take a look at the location A first of all. This is the location A. Okay. So location A is happen to be on upper surface. So let's say U is upper surface. Okay. So you're going to do the similar thing in lower surface also. L is a lower surface, okay? So just a notation. upper and lower surface. So location B obviously is a lower surface, but we are going to repeat the similar steps as we go through the upper surface. So let's take a look at location A on upper surface. So every subscript here, U, represent upper surface. Then every subscript L represent lower surface. Now, as you know very well from the last class, at every location or every surface of this airfoil, a 2D airfoil, this is 2D airfoil, isn't it? This is unit span, right? So you are looking at an infinite wing, and you cut off the unit span and pick it up as an airfoil. So this is airfoil, constant cross-section over the unit span, okay? So first of all, you are going to find out location A. Location A is right here, okay? Okay. Did I take the attendance of Stephen was here, right? Or you just came in?
Yeah, just came in.
Okay, yeah, sorry. Wait a minute, I thought I saw Steve. Anyway, so this is coordinate origin of S. Like I said, this is a curved coordinate, streamline coordinate system. This is origin. So you're going to measure starting from leading edge, distance to this location, distance to this location, same here. So starting from here, you are going to measure this much distance over the upper surface. This is S. Happen to be SA right here. Well, sorry. SU of A. SU. Okay? So this is SU. And then right here at that moment, I'm going to choose to take differential distance DSU. Okay? DSU. Differential distance DS. Now this DSU multiplied by unit span is going to get you area. This tiny strip area, DS. Okay. So now I'm squeezing out this DS. This is the area of a small tiny strip called DSU. Okay. This is area. So what am I doing here? So right here, location A, you have two things acting on it. One is the pressure, one is shear stress. Of course, you know that. Two things acting always at any location on upper surface or lower surface, either way. So this is a location A, happen to be upper surface. Distance S measured from leading edge. You have a pressure and shear stress acting on it. So suppose if you multiply pressure times this DSU area, what do you get? P times DSU gives you the force, which is perpendicular to the surface due to the pressure on this area. If you multiply tau multiplied by DSU, what do you get? Which is the force which is parallel to the surface of this area. So you have two different kind of forces acting on over all the surfaces. Happen to be right here as perpendicular and parallel component of force acting on it. Okay, so far. Go ahead.
Shouldn't the area be multiplied by the unit span of L? So it would be DSU.
No. I mean, distance multiplied by unit span gives you area.
And the name of the area is DSU.
Because it's DSU times 1. That's why.
Got it. Okay.
DSU times 1. Okay. Go ahead.
Where the streamline coordinate starts from that origin, is that the
Leading
stagnation point?
Yeah, leading edge. LE. Usually. But you can start from anywhere, but in this case, leading edge. Okay. Anything else? Go ahead.
What does the SU mean again?
Which SU?
SU, the one that's
SU, which one?
the one that's underneath that.
This one?
Yeah.
This is a distance to the location A. Yeah, that's right. Okay. So next thing is, okay. So I need to be zooming in a little bit. So let me just zoom in to location A. Then I'm going to color code. Be careful about that. So I'm going to use maybe purple. Okay. So this is PU times, sorry. This is, yeah, okay, sorry about that. I don't have to erase it. So this is a PU. PU is a pressure, and pressure is a function of SU. Do you understand that? Because pressure is a distributed pressure. So it's a function of location. So right here at the location A, PU happens to be PU of certain value. It's a function of SU. So, okay, so that means I'm going to use purple. So this thing is, suppose if you take a PU times DSU, this is a force, right? And this thing, tau u DSU, that's going to be also a force. Force due to pressure, force due to shear stress, acting right here on location A. Do you follow so far? Okay. And, okay. I'm running out of color, but let me use like this deep red. So I'm going to break down this force into two components. Okay? Two components. One is this component. Okay? Once again, I'm going to break down this tau u into two components. Two components. And then one of them is this component, deep red. And the other component, I'm going to pick up probably deep green. And then the other component is this component, right? The other component is this component. All right. So let's figure out component-wise what this thing is. This is PU DSU sine or cosine of theta. What's
Should be
that?
minus
What's this force?
PU sine.
So this is a PU DSU sine or cosine?
No, sine.
Sine.
Sine of theta. And then I put the negative sign because it's in negative x direction. Okay. Okay, so far.
Yeah.
How about this then? This is tau u DSU sine or cosine of theta.
Cos theta.
This is a cosine theta. Isn't that right? Tau u DSU cosine of theta. Yes. How about, let's just switch it to the deep red because I color coded. What is this force?
Minus PU.
This is a PU DSU sine or cosine. Cosine of theta. This is a negative because it's negative y direction. How about this thing? This is tau u DSU sine or cosine of theta. Sine theta. This is negative because it's in negative y direction. So you come up with four different forces. Those are components which is broken down into either perpendicular or parallel to the free space. Actually, perpendicular and parallel to the code. What am I doing? If you add those up, isn't that represent normal force?
Yeah.
Normal force contribution of this point A. If you add this and that, isn't that going to be actual force? Actual force contribution of this point A. This contribution of two different kind of forces, normal force and actual force, happening all over the place, over the surface. This is just happen to be point A. Okay? So let's just zoom out a little bit. I'm talking about, okay. And that first, okay. So I'm talking about dnu prime. What is it? This is differential normal force developed at upper surface per unit span at the location A. Which is, you just add them to both. You're gonna get this. Right? Normal force is a force component perpendicular to the code. At this location A, this is a normal force. That is, those two forces added together, right? Right? So what is it? Minus PU dSu cosine theta minus tau u dSu sine theta, correct? Of course, those two forces added together is going to be a contribution to the normal force per unit span upper surface. It's just a location A, but you need to imagine those kind of contribution happens all over the place, from leading edge to trailing edge. Go ahead.
So, did you say that's the normal force?
Normal force, yes. Normal force is a force perpendicular to the code.
Oh, to the core, okay.
Code. Yeah. Okay. Relative to the code things. Code. How about the other one? I'm going to switch to green. We're talking about the AU prime. What is that? This is the differential element of the actual force on upper surface per unit span contribution of the location A. How do you get such a stuff? Go ahead.
Wait, I have a question.
Go ahead.
Wait, did you say differential element or area?
I'm talking about differential element. Area. Yes.
Area?
Area. Yeah.
Oh, area.
Because this small tiny differential area, those two forces are acting on.
Okay.
Yeah. This is the contribution of position A only. Differential area we're talking about. Go ahead.
Your dAu prime should equal tau u dSu cos theta minus PU dSu.
That's right. Those two added together. That's right. So now let's go to green. This is dAu prime upper surface. Is those two forces added, right? So it's going to be minus PU dSu sine theta. And the plus. Oh, this is plus. Okay. Tau u dSu cosine theta. Oh, okay. Interesting. Now let's talk about a little bit different thing. So if you go back, okay. Let me zoom in a little bit more here. If I zoom in back in here, think about one. If you're talking about leading edge, any location is fine, but for a moment, let's choose the leading edge. This force, does it create moment around leading edge? Think about that.
No, no radius.
Okay. Does this force create moment around leading edge? Yes or no?
Around.
Around it?
Around leading edge. This force, does it create the moment around leading edge?
Yes.
Yes.
Oh, of course. Is it pitch up or pitch down?
Good job.
Pitch up moment. This actually creates pitch up moment,
Yes.
right? Pitch up is positive, okay? For a moment. How about this then?
No.
Pitch down?
It's-
Pitch down moment?
Yep.
Yeah. This is a moment.
Oh,
How about this?
Pitch up.
Good job.
I don't like this. Yeah, I don't.
Yeah, your error should be a little higher.
Yeah,
Because
Yeah,
As long as it's not, you know, on the trailing edge.
Okay. So I messed up. Sorry about that. I don't like it. Let me erase this. So what should I have done was not this. Okay, sorry. Let me draw.
just make it higher.
You have to change this in the red one too.
So it is actually if I use the green,
This is
this is it.
Yeah.
Yeah. Right. Sorry about that. Yeah, I always do. Every semester I do. So this is it. Okay. And then I go like this. Okay, this should be this, isn't it? Right. This should be this, isn't it? In other words, I'm breaking down this force into two components just like this. Sorry, this is better. Okay, how's that? You follow? So this force
Sure.
is broken down into this and that. This and that. It's the same meaning. Okay? Sorry about that. I apologize. I always do that every semester. So now, once again, so this force creates the moment at the reading end, yes or no?
Yes.
Yes. Is it pitch up, pitch down?
Pitch up.
Pitch up. Okay? This is moment arm. How about this?
Pitch up.
Pitch up.
Pitch up. This is a moment arm. So let's talk about moment arm. Okay? Moment arm is. Go ahead, Robert.
Does that mean that the green little arrow for the PUSU should be on the top?
Yes.
Yeah, it should be on the top.
This is one of the components of this force.
Oh, it's acting on that.
This way, yeah.
Yeah.
Well,
You can't really put it on top. Doesn't make
Huh?
sense.
what are you talking about?
Like you can't put it on top of the
If you
triangle.
put on top of it, it's misleading because
Yeah.
that's not the location of the point of contact. This is the force acting here.
Yeah.
So if you break down this force into two, each one of those component forces acting right here, point A.
Yeah. Okay.
Those two, point A. Okay, so it's misleading. So I should have done this to begin with. So this is a momentum. Okay, let's call this X. This is also momentum. This is Y. Do you follow that? So momentum is associated with each one of those four different kinds of components of forces. This force multiplied by Y creates moment around leading edge pitch up. Do you follow? This force multiplied by Y create pitch down moment around leading edge. This force multiplied by X create pitch up moment around leading edge. This one multiplied by Y create pitch up moment around leading edge. Do you follow? So you have like four different moment contributors.
And then the
Let's just find out those. Okay? So let's just find out those. So I'm talking about, okay, B, moment leading edge prime. U. Okay. All right, sorry about that. DMU prime. Leading edge. I'm talking about leading edge moment. Okay, so this is going to be PU cosine theta plus tau U sine theta multiplied by X. X is the momentum. DSU plus minus PU sine minus PU sine theta plus tau U cosine theta Y DSU. Do you follow that? Just to zoom in a little bit and think about it for a moment. So those two forces multiplied by X momentum, that means this force and that force. creating moment around leading edge. Those two forces, one is actually negative contribution. Added together, multiplied by y, that means this force, that force. One of them is negative. Okay? Creating leading edge moment. This is a contribution to the leading edge moment creation at the location A. Okay, so far. Go ahead.
So, pitch up is positive.
Pitch up is positive. Pitch down is negative. It's usually airplane notation. Pitch up positive, pitch down negative. Okay, so far. Everybody, are you following? This is something you have to do in wind tunnel. Guaranteed. Go ahead.
Why aren't there more negatives with the,
This one?
well, I feel like there should be more negatives, because like in the top two, we
Because pitch up is a positive, pitch down negative. So this is what, PU sine theta, PU sine theta y is
Pitch down.
pitch down. Pitch down, that's my negative. Go ahead.
Shouldn't the two top be negatives? No, because they create pitch up.
Because it's pitch up, it's positive. Let me double check. Yeah, those are both pitch up. One of them pitch down. Only one thing creates pitch down, that is this thing.
Oh,
This is going to create pitch down. Everything else pitch up.
that's.
Yeah, that's fine. Okay. So make sure you understand what I'm doing. Okay. So let's do the similar thing. I'm going to switch it to probably black. Okay. So this is all upper surface, right? Similarly. Yeah, that's right. Yeah, that's right. Similarly for lower surface. You can do such a thing because I'm kind of, well, of course you can go over all the details by yourself, but the lower surface you can do the similar thing. So in other words, you can have dn L prime, which is equal to TL DSL cosine theta minus tau L DSL sine theta. Similarly, also another similar manner, dA L prime, dA L prime. This is PL DSL sine theta plus tau L DSL cosine theta, and then DML prime leading edge is equal to minus PL cosine theta plus tau L sine theta x DSL plus PL sine theta plus tau L cosine theta y DSL. Same thing. So I'm repeating the same process on upper surface, lower surface. It's the exact same process. So this is essentially upper surface. Okay? This is lower surface. Okay, so this is a full detail of pressure and shear stress contribution to normal force, actual force, leading edge moment, differential area. Go ahead.
Why did we choose the leading edge to take the moment? Why not? Like
You can actually take the leading edge moment and then move it to quarter chord or half chord or trailing, and you can do that freely later. So you're going to pick up one coordinate. In this case, I happen to choose leading edge because it's easiest.
Okay.
Okay. You're gonna learn how to convert leading edge moment to the quarter code, to the half code, or anything. Yeah. You can freely move around. Go ahead.
DS like derivative? I don't understand what that means.
It's a differential area.
Differential area.
This is the yes.
Oh, okay.
Yep. Anything else?
Shouldn't those equations have a negative in them? Because when you take the sine and cosine, they would actually point in opposite directions for each component. When you look at for the lower.
Yeah, so basically the sign convention wise, okay, the direction of the force follows through x and y.
Right.
In other words, positive x is plus, negative x is negative.
Yes.
Now, moment, pitch up is positive,
Yes.
pitch down negative. So in this case, left-hand side coordinate, that's why.
Ooh.
Sorry about that, but I want, well, because, you know, it's Professor Anderson's fault. He wants to make everything pitch up is positive, pitch down negative. So this is left-hand side coordinate. So that actually is a little bit confusing, but you have to follow through. Pitch up is positive, always, airplane-wise, in aerodynamics. Go ahead.
Would you be able to scroll back down? Yeah, great.
Equations, okay, so. Yeah. Any other question? Yeah, go ahead.
But still, shouldn't in DAL prime, shouldn't PLD SLL sine theta be negative? Because it's going to the left instead to the right.
Yeah. Lower side is essentially, you are going to, lower side, you have to be very careful because this is a notation positive theta versus theta, that's one. So it's slightly different from upper side.
Okay.
Lower side is different, a little bit. Yeah, so let's be careful about the notation of the direction of theta. This is positive theta, positive
Oh,
theta.
I see it.
Yeah, that's,
I got it.
that's opposite, that's right. On lowercase. Any other question? Go ahead.
So the dn is the normal force per unit span.
That's right. dN is a normal force per unit span and over the ds surface. In other words, those equations are on the location A.
Yeah.
Every other location contributes similarly, just like this. I'm just picking up location A.
So
This is location B, by the way. Location
what
A.
dA would be the shear force then?
Shear force is tau. This is an actual force. This is normal force. In other words, this is the force developed in the direction perpendicular to the code. This is the force developed direction parallel to the code. And then those are the forces created by pressure and shear stress distribution. Go ahead.
Would you integrate those statements together?
That's right.
Yeah.
Next step is of course integrate from
Okay.
leading edge to
Fun.
That's right. The point is being, we have to integrate those from leading edge to trailing edge on upper surface, lower surface. Then what do you get? Normal force, actual force, leading edge moment. That's what you get.
Yeah.
That's what you get. That's the next step. Can I move on? Go ahead.
So the fact that you mentioned of actual force, is that the same as the dA? Because you said before. You
Why
said,
dA is actual force?
no, that's what you said.
Yeah, DA is actual force. But
Yeah,
what is DA?
Differential area.
Differential area is DS.
DS.
Listen.
Okay.
I hate to go back, but this is something I'm talking about, okay? This is actual force.
Oh,
This is normal force. That's what we're trying to find.
okay.
And also leading edge moment. Okay, moment could be anything. In other words, those two forces can be shifted around along the code. Okay, if you put those two in right here, it's going to be leading edge moment associated with. Okay. Let me move because I hate to say today we covered only one page. I hate to say that. So what's next?
Integration.
Integrate, yes, of course. So you're going to basically integrate, and then before actually start integrating, you have another step. What do you mean? Oh, that means dN prime. This is the differential normal force developed by contribution for both
Some your upper and lower.
upper and lower. right?
Yeah.
And then dA prime is dAu prime plus dAl prime, and then dMLE prime is dMu prime leading edge plus dML prime leading edge. Then let's integrate. From leading edge to trailing edge. Let me tell you, we're gonna literally do this in your project upcoming mathematically. We cannot avoid this. So next page is this, integration. Integrate from leading edge to trailing edge. Upper surface, lower surface. You've been taking notes, you don't have to. I mean, everything's given there. Well, if you took the notes, great, because it's a running process, but everything's given. Anyway, so this is leading edge to trailing edge. Integrate upper and lower surface to get any. This is what? Normal force per unit span. So this is actual force per unit span you develop on this cross section.
We get normal and axial forces, but how do we know where they act along the chord? Like,
Because we resolved using theta. Theta is basically that is the surface. In other words, theta depends on the shape. Right?
oh, and that's a geometry thing.
Geometry, yeah.
Okay.
So theta at each location depends on your shape. So by using this cosine theta time, you're going to resolve all the forces in this way on
You
that
can
way.
get it as a function of theta, and you can just plug it in.
That's right. So this theta depends on your shape.
Yeah.
Yeah.
Okay.
That's right.
How about that?
So you're going to do integration from leading edge to trailing edge. You get normal and actual leading edge moment per unit span. This is the whole process. And then, and only then, if you know angle of attack, in other words, what is the angle of your test model in your wind tunnel? 10 degrees? Of course. Then you can get lift and drag per unit span. This is the entire process of wind tunnel testing based on the pressure measurement. You gotta do this in wind tunnel. Mathematically speaking, this is a full detail. This is rare because probably most professors never cover this kind of thing. This is the mathematical detail of what you need to be doing in wind tunnel in the future. Come back to this page, okay? All right. Any other questions? So we're gonna stop here. The next class after this fall break. Next class is after the fall break. We're gonna pick up from page 6. Okay, we're gonna see you on Wednesday for midterm exam.
What? Yeah, pretty much what we're gonna do at this room.